There's a quiz. I'm just going to log in and make it visible. 66.2%. I think that's much better. Much better than 50%. How was that as a quiz? Was that better? Yeah? Cool. All right. Hopefully, no. Did anybody get 4 of the same type of question? Okay. You did? Almost? 3 out of 4? Oh. All right. Okay. So, right. So, anyway, we should cover some actual material today, shall we? Oh. Not supposed to touch that end of it. So, we recording? Good. So, I wanted to dip once again into a topic that's going to be relevant to upcoming laboratory procedures. I wanted to talk to you guys on the subject of digital and analog conversion. To what extent have you guys already done this topic in previous classes? Did you guys cover A to D and D to A? Not at all? Excellent, we're breaking new ground. So, roughly speaking, very introductory, I presume all of you know of the existence of both digital and analog signals. Good. We're getting somewhere. Obviously, in order to read an analog signal by a digital microcontroller, it is necessary that that analog signal should pass through some kind of circuit in order to be digitized. We're going to discuss specifically the types of technologies that are used for this type of thing, what the trade-offs are of the various ways of going about doing it, and we're also going to talk about some additional matters related to sampling and how one goes about reading electrical signals and some of the pitfalls that can happen therein. I have prepared 26 slides. I have 25 minutes, so probably we won't get through all of it, but I also haven't done the section on digital to analog conversion just yet, so, you know, this should probably be a 2 or 3 lecture. Cool? Awesome. Maybe I should light it up for emphasis. Yeah. So, you know, this is actually like the first time I've presented this type of slide that I've made in person. That's cool. I like this whole in-person class thing, but I'm, you know, yeah, anyway. So, again, this should be assumed knowledge. When working with electronic systems, we have analog and we have digital signals. Analog signals, of course, have any voltage value between 0 and whatever your reference value is. In fact, you can go above that as well, but generally speaking, we're concerned primarily with voltages that are sort of inside of the voltage range of the electronics that we're dealing with. Digital signals, of course, are either on or off, high or low, 1 or 0. So another way of conceptualizing this, which is important, with digital electronics, the information is contained entirely in whether it's a 1 or a 0. There's no other information which is pertinent to the circuitry. Analog signals, on the other hand, you can think of them as electronic signals that are always carrying information because the actual voltage level itself is what you're interested in, right? So, like there are various different types of, we'll get into some examples. So, yes? we think of digital signals as being discrete, and we think of analog signals as being continuous. Discrete, and like we're talking in the math terminology, right? Like discrete functions versus continuous functions type idea, right? So far, so good. So, let us consider a real-world application of digital to analog conversion, and back again, in the reverse order. So, consider the following industrial application. Let's say that we have a hydraulics system where the position of a hydraulic cylinder is determined by an input control such as a turn knob, right? This is what a potentiometer looks like. You guys have seen potentiometers before, I assume? Yeah. Have you seen linear potentiometers? Or just the rotary ones? Yeah? I get a lot of blank stares. They're not just rotational, you can also get potentiometers that are like linear. When you guys get into 3DX4, the labs in there's a ball and beam system where it's really cool. Well, anyway, I should describe what a potentiometer is first before I get into that. But anyway, so this thing outputs an analog signal, which is the position of the knob is output as an analog signal. It is a voltage. The power going to a DC motor would also be controlled by an analog signal, right? Like there are different ways of doing it, but let's just imagine right now that we have a very simple DC motor. All we want to do is control how fast it's spinning or what the torque is on the motor by how much voltage we apply to it. The voltage level needs to be controllable, right? So that is an analog output. If we want to wire that to a controller, we're going to have to take this guy, convert that to a digital signal, do our processing on it, convert it back to an analog signal to run the motor with. Any questions so far? Yeah. I mean, right? So far, so good. So, have you guys done, have done potentiometers, like electrically? No? Excellent. Wonderful. So, a potentiometer is a variable resistance resistor. How it works, you have a resistive material that has a wiper or sliding contact which slides over the surface of that resistive material. This is, of course, low resistance, the bit in the middle is high resistance. So essentially, what you have is it's a voltage divider, like voltage dividers, right? It's like a voltage divider, but the position of the wiper on the resistive material determines how much is in the upper resistor and how much resistance is in the lower resistor. Thus, the level of voltage on the sliding contact is proportional to the position of this slider across the resistor. Make sense? Question?
Where did you say the point of high resistance was again? In the middle or on the left?
Yeah, the squiggly bit.
The point of highest resistance, sorry.
Oh, sorry, not highest resistance. This is just a resistive material.
Oh, I see.
So now I'll talk about that thing that I wasn't going to talk about until I got to this slide. So you're going to take a course called 3DX4 Control Systems. This is a lab course, and one of the apparati that you will be using in this course is called the ball and beam apparatus. So what it is you've got a metal rod, a ball bearing, and a strip of this resistive material, right? The metal ball forms the contact point between this low resistance conductive material and the resistive material. right? So the thing that makes this interesting versus like a regular potentiometer that you turn is that you're able to control the tilt of the thing. So the act of gravity on the ball will move it across the wiper, and the thing that you're trying to accomplish in those control labs is to get it so that you move. This thing is kind of hooked up to a motor mechanism here. You're trying to get it. You're trying to design a system so that you can have the ball acquire any position upon this rail apparatus, right? And it's, you know, it's easy to do-ish when you have feedback mechanisms installed, but that's kind of another course. But this is the technology that's used to determine the position of the ball in that lab, right? Potentiometer. So, yes. So, the resistance inside of this resistive material is dependent on the distance the electrons must travel through the resistive material, right? So, like, if I have a strip of resistive material and I touch it with a conductor here, I have all of this resistance on one side, all of that resistance on the other, right? And so, you know, if this whole thing is, you know, 100 kiloohms, and, you know, it's 40%, you'd have 40 kiloohms on one side and 60 on the other, right? Kiloohms, there we go, right? Make sense? Yeah, good. And you can see how, like, if you applied high voltage to one side, low voltage to the other, you would get a voltage here that was, you know, according to that ratio, right? So this is like the simplest example I could come up with of a analog input device, right? The question is, how do we get a microcontroller to read the position of a potentiometer? Because that's like the mother of all control applications, right? You have to be able to take inputs. Do you have a question? Oh, sorry, yeah, okay. So, the amount of resistance per unit length can be controlled by controlling the cross-sectional area of the material and the resistor. By introducing a third sliding contact to the resistor, we can create a device where resistance is variable and based on the position of the sliding contact. Both linear and rotary potentiometers work this way. The example on the previous slide, this is a rotary potentiometer. The ball and beam example that I gave you, that's an example of a linear potentiometer. Good. So these things output in analog, right? You'll get a voltage which is somewhere between 0 and +5 if you apply +5 to it, right? Good. So here's a question. If we have this thing which can output a certain level of voltage, why do we not just use that directly to control the motor? Right? Like, even if we don't consider our industrial example of, you know, some sort of hydraulic machinery, if you sort of consider like one of these tiny little DC motors that you can, you know, pick up reasonably cheaply, why wouldn't you just have a potentiometer, divide the voltage, run that voltage straight into the motor? Yes?
Would that draw too much current through it, which might mess around?
Yeah, well, it might not be enough current is the problem. It depends on how much resistance is in the resistor, right? Anybody else who hasn't read the slide yet? So it's also a power dissipation problem, right? So if you have two objects, right? One of them you're using to consume, say, 50% of the voltage, right? The other is the motor, which is consuming the rest of the voltage. The resistor is dissipating as much power as the motor is. What do resistors do when they dissipate power? They heat up. Very correct. So, basically, yeah. Motors also tend to draw power. It's like it's not necessarily current that you're interested in, it might be wattage, right? So the power that the thing draws is, of course, the voltage times the current. If it's drawing a lot of power, it's going to need more current. You probably don't want high levels of current traveling through a device that people's fingers are touching, right? Just not a great idea, right? So what do we use instead then? Well, for acquiring the position of the potentiometer, we use standard low power, low cost digital electronics. And of course, the types of things that we're going to be talking about in the analog to digital conversion section right up there. So, once we have acquired and digitized the position of the potentiometer, we can take that and then we can run it into a controller. The controller can decide from that how much voltage it needs to apply to the motor to do what it needs to do, i.e., you can put a control system in. Now, you can also do this with electronics, of course, because anything, like in this class, pretty much anything you do with software, you could also do with hardware if you wanted to, right? But, you know, it's often desirable to have reprogrammable controllers. So, if you want a DC motor to acquire a particular position, do you apply a constant voltage to it? I see some shaking of heads. No. What do you get from a DC motor if you apply a constant voltage to it? What is constant about that motor?
The rotation?
Hmm?
The rotation?
Angular velocity. Yes, absolutely. So if position is what you want to control, just running voltage to it isn't going to accomplish what you want to accomplish. So, once the controller has decided how much voltage should be going to this motor, you can then take that digital signal, because it's coming from digital electronics, run it back through a digital to analog converter, and then, of course, you'll want to put it through some kind of device which separates the power supply for the motor from the power supply for the digital electronics. It's very important to isolate those. If you try to run a motor off of a GPIO pin, you're just asking for trouble, really. So in sort of the low-power DC, tiny DC motor applications, the types of things that you would use is a power transistor. Very similar to a regular transistor. The only difference is it's bulky and it can handle the kind of current that's necessary to be able to run that thing, or run that motor, right? In higher power applications, you're looking at something like a relay, right? Probably a relay, reasonably fast, like a pulse width modulated signal running through a relay that's then run through a low pass filter. That would smooth the signal out so that you would get a regular sort of thing. But, yeah. Any questions so far? Good. So, to the subject of reading voltages. We are thus presented with the problem of converting potentiometer wiper voltage to a digitized signal. We have analog to digital conversion, and we have digital to analog conversion. In the case of analog to digital, we are essentially going from one wire to many, right? In the reverse process, we are going from many to one, right? So, essentially, what a lot of these circuits are going to look like is, how do you take this one thing and derive a whole bunch of things from it, right? Yeah. Analog signals use one line, but digital signals use one line per bit. Thus, ADC is a many-to-one problem. Digital to analog is the reverse. Yes, this is a short slide. Any questions so far? Okay. So, So when we start talking about how to read analog signals, we are instantaneously presented with a problem. When? When do you take that signal? Right? So we will want to do it periodically, right? Because we do everything periodically. We can't do it continuously because digital electronics are not continuous, they are discrete. So we must sample the incoming analog signal. Does that make sense? So, yeah. So this is a process by which the analog signal is discretized so that it can be later digitized. So what we do when we are reading an analog signal, we sample it at certain points, and then we have a small circuit which holds the sampled value while the ADC is working on it so that that signal doesn't change during conversion, right? Because you can imagine, if you're performing a conversion operation, which incidentally, a lot of them take several clock cycles, if you're performing this conversion over time and the signal changes, like say the signal loses 30% of its value by the time you get to the end of the process, right? What's your output going to be? Nonsense, that's why. So it's important that you not only sample the data, but you also hold it so long as the next sample hasn't come in. Does that make sense? Good. Good. So, yeah. So, digital signals, of course, because of the clock signal, and we consider digital signals to be valid at the point of the rising clock edge, right? And at no other time. Most of the time, anyway. Analog signals, of course, they aren't, so they can do whatever they want. Yes. Digital electronics would only be able to read an analog signal with a fixed frequency anyways. So this is what it looks like, right? If we have an analog signal, which is coming in, we take the value of this at certain points, right? That's the sampling. And we hold that until the next sample comes in. That's the holding, right? Sample and hold. In general, at some specific frequency, i.e. the sampling frequency, the analog to digital converter system acquires the current voltage level. The value is held until the next sample occurs. The smaller the sampling frequency, the more closely the digital output signal resembles the input signal. So, I'd like to show you a cool, nifty little online tool which demonstrates this pretty well. That's big enough? You guys can see it down here? So, I hope so. So this blue line here, this is an analog signal which is being read. It's actually it's the sum of these three signals, right? Get back there, you. Thank you. So, watch what happens when we increase the sampling frequency. The higher the sampling frequency, the more closely our data resembles the incoming signal. Right? This is actually known as discretization error. So the error that's introduced when you discretize the analog signal is known as discretization error. If you pull this back down, you can see it gets quite bad at very low frequencies, right? So it turns out, oh, and incidentally, you also get better resolution when you increase the number of bits that you're converting with, right? So right now, this is they're using 5 bits on this. If we decrease this, you can see, to 2 bits, basically we've only got 4 distinct levels that we can be at here. If you decrease it down to 1 bit, you're essentially just, comparing it to a reference voltage and deciding high or low. If you increase that, you get, again, better and better approximations of the actual signal. Make sense? Question?
Why is it necessary to then use lower sampling frequencies in certain applications? Why don't we just go not sampling frequency all the time?
I'm so glad you asked. So the question is, why wouldn't you just go as high as you could, like all the time? Why wouldn't you use all the bits? Why wouldn't you use all the frequency? The answer, of course, is power, right? The higher the frequency with which you're sampling, the more often you're running the circuitry that performs the analog conversion. And for many applications, you don't actually need to do it that fast in order to sort of meet the requirements of the system. Consider, for example, voice. Can anybody in the room tell me what the frequency range of the human voice is? 8
kilohertz.
8 kilohertz, roundabout. Yeah. Very good. So let's say anywhere from 4 kilohertz to, say, 50 kilohertz. Audible range, right? Audible range, I think, goes up to like 100 kilohertz, something like that, maybe. I'm not sure. But anyway, 100 kilohertz is actually not that fast relative to digital electronics, right? So if you sample, like, you don't have to sample much faster than that in order to be able to perfectly reconstruct sound waves. And the reconstruction of sound waves, as I probably don't have to explain, that's a pretty big application of electronics. Lots of people are interested in sound. Who here doesn't listen to music? Who here doesn't talk to people on the phone? Right? But yeah, so you don't, if you don't need that much frequency, you're just using power that you don't need to use, right? So, yeah. Let me look at the slide, see if we, yeah, okay, fine. We can't get into the next topic, so that'll be enough for today. Thank you very much for your time and attention, folks.